We're next going to take a look at another application for stacks that involve method calls. Let's suppose we have a program that calls a very simple method. Now, whenever we actually make a call, the current method or the current program or method, wherever we're at, usually has different variables that are local to that calling routine, which we call local variables. That needs to be saved by the system somehow, because if we don't save the values of those variables, the new method is going to overwrite our memory, which means we're going to lose the values of those variables. So every time we make a method call, we need to save all the information that's currently stored at that point. That way, whenever we get back to that method, we have those values back. We also need to know the current location of that routine, because if we call a method, how do we know when to go back? We've just been assuming at this point that, oh, the computer knows exactly where to go back, but we need to be able to say, here is the instruction that you would go to in your code to do that. So we need to store that information as well. Well, all that information is usually stored in what are called machine registers. Now, we'll talk more about registers in other classes, but they're just these specific places in memory that allow, I shouldn't even say it's memory, they're not in memory, but they're specific memory locations within our machine that will allow us to store this type of information. Now, the problem with registers is that we have a very small number of registers. There's usually like 31, 32, something like that. It's a very small number, so we can't store everything in those registers. The way we can handle this is we can use a stack to take care of storing all the information within a method before we make a method call. The idea is whenever we do make a method call, we take all this information, such as the register values and the return address. The return address is where we go when we're done with the method, but we take all this information and we store it on the top of the stack. We'll then transfer control from the current method to the new method that we just called. And now, since all that information is stored somewhere else, we're free to replace the registers with the new method's values as it sees fit. In fact, every time we make a method call, we just push the current information in the memory onto the stack. So if we make another method call, we'll take that information and we'll push that onto the top of the stack. If we make another method call, we'll push that onto the stack and so forth. And then whenever a method is going to return, we go back to a previous method call. We take the information that's on top of the stack and we store that back into our memory and back into our registers. That way we preserve everything that we had in the method call and we store it back into the memory registers when we're done. Once we've done that, then we'll take the jump to return to the previous method call. The information that we save in this case is what we call either an activation record or a stack frame. Now, like I said, every time we make a method call, we can store more and more information. This means it is possible to keep calling methods and keep adding more information onto the stack. The problem, though, is the stack has a finite amount of space, so eventually if you keep calling a method forever, you're going to run out of stack space. So if that does happen, we will get a fatal error. The system will crash. Usually it's like a stack overflow error or stack overflow exception, something along those lines, which simply means you called too many methods and you can't store any more information. We're now going to briefly introduce the idea of recursive methods. Here's an interesting question. Is it possible to have a method call itself? And the answer to that is yes. I think we talked a little bit about it before, and we'll be talking a lot more about it later on the course, but this is what we call recursion. The idea with this is that we have a method call itself. So we're allowed to do that. The catch, though, is if we're not careful and we just keep calling the same method over and over again without any changes, we're going to get that stack overflow error because we're going to keep adding stuff onto the stack. The idea with recursion is that every time we make a method call to itself, we change the argument a little bit such that the problem that we're trying to solve gets smaller and smaller, and eventually it's going to get easier to provide an answer to that particular problem or giving a solution to that problem. Here's an example of a method that uses recursion. So here we're going to print a list, and we pass an iterator, so we pass the current position. So what we do in here is we first check, is there another item in the list? So that's what the iterator.hasNext does. If there isn't anything, then we're going to return and we say we're done. Otherwise, we're going to print the current item of the list. And notice that when we call the next right here, after we print, we're getting the next item in the list, and then we're going to call print list again. So that's what we're doing right here. So we're calling the method again, and we're passing the iterator, but at this point, we're actually sending the next item of the list with our iterator. Now, this particular method works just fine, no major problems yet. Emphasis on the yet. The idea with this, as I mentioned, is as long as we're not at the end of the list, we just print the next item in the list, and then we're going to call the method again. We're going to call itself passing the iterator. So each time we call it, we're going to take one step closer to getting to the end of the list. Now, here is the problem with it. Let's say we have a very large list, maybe 20,000 elements. That means that we're going to be calling this method 20,000 times. There will be a stack of 20,000 activation records that represent all these nested calls. If you're calling a method that many times, there is a very good chance that we're going to run out of stack space, and then we're going to get an error. This particular recursive method is an example of what we call tail recursion. And this is not a very good form of recursion. The idea with tail recursion is the recursive call is done at the very end of our method. It's the last line. And the point here is it's not really necessary because we can simply eliminate the recursion altogether by using a while loop. We'll talk about this later on, where we can use either while loops or use recursion for solving problems. But for tail recursion, we can just create a while loop, and instead of having the recursive call, we just have the particular assignment per method argument. So every time that we would call a method, instead we would just use an assignment to take care of it. And this would actually simulate the recursive call, because with tail recursion, we don't need to save anything after the call. So nothing needs to be saved after we've done a particular iteration, so we can use the assignment to override what we were doing with each method call. And then whenever we were done with the call, well, we didn't need to know anything about the saved values, so there's no need to actually put anything on the stack, because when that method is done, the information that's on the stack isn't necessary. We don't need to save it because we're not going to use it again. So what we would do is we would just go back to the beginning of our loop and just pretty much repeat the same process as if it were a new recursive call. Let me show you an example of the same method, except now we're replacing the whole recursion part of it with this loop. So we have a while loop that says while true. Now granted, that's an infinite loop. Usually infinite loops are bad, but you'll see why this is okay here. All we're doing inside here is we're checking if there's something next, we'll print whatever that is, and then we go back to the while loop and then we check that again. But whenever we get to the end of the list and itr.hasNext is false, so in this case, if not itr.hasNext is true, we're going to return, which means we completely get out of the while loop, we get out of the method, and we say that we're done. We can do this with a single method call, and we didn't need to use tail recursion. That particular example was pretty easy to do. In fact, removing tail recursion is so simple that some compilers do that for us automatically. In fact, it's even possible to completely eliminate recursion altogether. We can take a program that uses recursion and we can rewrite it so that it just uses loops instead of method calls. The trick though with that is you really have to understand the data that's being passed with each method call in order to make that work, because every time you make a recursive call, that information is being stored onto the stack. Sometimes that information is needed after the method call, so you can't just do exactly what we did with eliminating tail recursion. So if you're careful with how you handle that data, then you could just not use recursion at all. But what we will see later on in the course is there are a lot of benefits to using recursion, in that we'll be able to solve some very complex problems with just a couple of lines of code.